For the second part of Ken Golden's talk, and that will conclude the program for today. So here's Ken.
Okay, thank you. Before I start with the second half, I forgot to show you a little movie of the X-ray tomography of the brine inclusions. So you can just get a more three-dimensional perspective on this. Oops. Okay, so now you see them rotating. You kind of see the layers. This is the disconnected, that's right around the percolation threshold, and this is well above it. And you see the kind of the layering between the ice platelets as to how the brine arranges itself. So it was kind of similar to the movies that you guys were showing. So okay, let's get rid of that. Okay, so now we're going to go here. Okay. Okay, so ostensibly, what I'm going to talk about is kind of motivated by the remote sensing problem. However, what this is really about is sophisticated methods of homogenization for some of the transport properties that you guys are interested in, that we're interested in. So the basic remote sensing problem for sea ice is effectively an inverse problem, where given bulk electromagnetic data, such as the complex permittivity of the sea ice, we would like to recover the properties of the ice. In particular, on the micro scale, say the brine volume fraction, also, if we could, information about the conductivity of the brine inclusions and their separation and so on as it warms up. On the larger scale, of course, I mentioned the problem of sea ice thickness is one of the holy grails of climate science, and ice concentration, there's a lot of great data and a lot of great methods for finding that. Okay. So back to the basic homogenization setup, but now we're considering complex parameters, in this case with an interaction with electromagnetic waves, in the so-called quasi-static limit where the wavelength is long compared with the microscale. Same setup, instead of J equals sigma E, displacement equals the permittivity times the electric field, divergence free, curl free, and then the the local constitutive law becomes the macroscopic constitutive law relating the average D field to the average electric field through the key effective transport coefficient, in this case the effective complex permittivity, which then defines that parameter. And again, the effective complex permittivity is a very complicated function of the ratio of the constituent parameters as well as the composite geometry. And one of the main points of what we're going to do here, the kind of integral representations that I'm going to show you, are where these two fundamental dependencies, namely the parameters of the system and the geometry, are completely separated. And that's the power of the method, as you'll see. And we can apply that to lots of other problems as well. To give you some intuitive sense of this quasi-static assumption, this is a photo, and I've actually taken you'll see some beautiful video of this in the movie that I'll show you at the end. So some of the idea of homogenization, well, a long wave like this, in the order of, 40, 50 meters of wavelength, the long wave sees an effective medium. It doesn't see these little individual pancake flows. There's some effective propagation characteristics. And as I mentioned, I have a PhD student working on some of this. And there's been a lot of activity on this throughout the world, and a lot here, and especially in Australia. Yeah, Steve?
Do we know why the pancakes have the size that they do?
I bet there are people that do understand the length scale there. The fundamental issue is basically you got the grease ice and the frazzly stuff, and then the waves come through, so you get compression, and so it's got to have something to do with the initial formation, but I don't know. Okay, I don't know what determines that scale, but there is seems to be a fairly regular length scale associated with it, but I'm not the right person for that one. Okay, okay. So this method that I want to talk to you about goes back actually independently by David Bergman and Graham Milton. So Graham Milton is actually at the University of Utah. Independently with my PhD advisor, George Papanikolaou, I laid out the mathematics of this and proved the underlying theorems and the representation formulas. And so this is the analytic continuation method for bounding, for getting rigorous bounds, not on a real parameter like well, it can be complex as well, but the ones I showed you before, but in the complex case. So these would be regions in the complex plane that the effective complex permittivity is restricted to. And you want to exploit the analytic properties of this function m of h, the effective parameter divided by epsilon 2, as a function of this ratio, and that's a complex parameter. And so this analytic function, its domain of analyticity, it's analytic everywhere off the negative real axis, and it has a beautiful symmetry, a Stilch's property to it, where it takes the upper half plane to the upper half plane, the lower half plane to the lower half plane. And that's enough to give it these very beautiful ways of representing such a function in terms of very powerful integral representation, Stilch's integral representations. So again, this analytic continuation method, first the forward homogenization problem, basically where you have information about the composite geometry that is incorporated into these formulas through what's called a spectral measure that I'm going to talk a fair bit about. And then that gives information about the complex permittivity. And again, this is one of these fundamental methods or advances in homogenization. And so this is the integral representation for the effective complex permittivity. This is a slight change of variables, so now this function is analytic off the interval 0, 1, and so the measure, or all the singularities of the function, and anyway, as I said, this is a spectral measure of a very important self-adjoint operator on a particular Hilbert space, and it's concentrated on the interval 0, 1. And then the inverse problem, the inverse homogenization, is given the information about the bulk complex permittivity to invert for information about the composite geometry, volume fraction, separation information, and so on through this spectral measure. Okay, and just a little more detail about this. And again, one of the main points here and the power of the method is that all the geometry is in the spectral measure, and all the parameter information, the epsilon 1 and the epsilon 2, are in this complex variable. And this thing, it depends in sort of a fractional linear transformation dependence on S, and then as a linear functional, the measure, this is linear in mu. That plays a big role in how you actually get the bounds. So this spectral measure, the mu, is a spectral measure of a self-adjoint operator chi gamma chi, where chi is a characteristic function of the brine phase, 1 in the brine, 0 in the ice. And then gamma is a fundamental operator that when you manipulate the quasi-static Maxwell's equations, this is what comes out when you want to solve for the electric field to set up what's called a resolvent representation for it. Gradient, inverse Laplacian divergence. It basically acts like projection onto the space of curl-free fields. The mass of the measure is the volume fraction, the brine volume fraction. The higher moments depend on the endpoint correlation functions of the medium. So I worked a lot with these integral representations. A lot of earlier work that I was involved in with the Office of Naval Research, developing again rigorous bounds, complex versions of the arithmetic and harmonic mean bounds, the Hushian-Strickman bounds, tighter bounds than that, so-called matrix particle bounds. And we didn't derive those originally, but we were applying all this to the context of sea ice. Yeah.
So, out of curiosity, what are the properties of the static Maxwells that you need to be able to construct your gamma?
Curl-free is really important. Those basic equations. I mean, you basically play with those equations, and there's a long series of steps and manipulations one has to go through. But you start messing with that, getting the time dependence, at least in that problem, and things start to get issues. And that's part of the problem, for example, with the waves going through sea ice. That's really, in some sense, a more difficult problem, but we try to extract out and make as simplifying features that we can to get it as close to the quasi-static Maxwell's equations that we can to try to get into that form. Okay, so again, one of the key assumptions is the matrix particle assumption. And so these go well beyond the Hushian-Strickman, the arithmetic and harmonic mean bounds. This is a tighter set of restrictions on the composite material because those other bounds don't require that at all. The geometries are completely arbitrary. There's no assumption of an inclusion in a host. That's something new here. And so there's a parameter Q. These are like secure. So that's the brine, R sub B, the brine, and that's the ice. There's like little spherical shells of ice that protect the little brine inclusions from each other. And when Q goes to 1, that means they start to touch. And anyway, so we got these beautiful tight bounds actually we were the first, I think, to derive complex bounds for matrix particle composites. And anyway, so then the first step was to invert all that and recover brine porosity, which we were able to do. But then we were able to take this much further, I think in a very beautiful mathematical paper with a young man named Chris Oram, who's at Oregon State University now as an instructor. We were actually able to invert for brine inclusion separations from measurements of the effective complex permittivity through a rigorous inverse bound on a spectral gap that arises when when they're not percolating. And here you can see, so this is all electromagnetically derived. This is as the temperature increases, and this is increasing connectedness. The Q is approaching 1, and so you can see, so electromagnetically we can really see the coalescing of the brine inclusions. Just a little more detail on this. This was the original matrix particle assumption was investigated by a close friend and colleague of mine, Oscar Bruno. And so, in other words, we didn't solve the whole problem. We just construct algebraic curves in this PQ space, volume fraction and separation space, which bound the admissible region, and that gives us these rigorous bounds that we can then match up with all this interesting sea ice data and really see the coalescence of the brine inclusions. Okay, a really cool example of cross-pollination, which is where we've looked at the porous microstructure of bone. Actually, it kind of really looks like really looks like your case. And this is young, healthy trabecular bone. This is older osteoporotic, where basically the whole point is you are losing connectivity. The quality of the connections is decreasing. And so we essentially took our methods for sea ice and applied it to this case, to the osteoporosis, or to human bone, and we developed, based on these Stilts's representations and the inversion for the spectral measures, we basically developed a method for electromagnetic monitoring of osteoporosis and trying to look at the loss of connectivity, and hopefully non-destructively. So you don't have to cut somebody's bone open and, it's just with an electromagnetic wave. And the key thing here is, so these are direct calculations of that spectral measure, so I'm going to talk about that in a second, about given a composite geometry, how do we construct this all-important spectral measure? And part of what I like to say here is the math doesn't care if it's sea ice or bone. I give a lot of popular lectures, popularizing mathematics and so on, and so I think this is just a beautiful example that, again, the math just doesn't care. We could apply the same ideas to brain tissue or lung or kind of whatever composite that you're interested in. This is a reconstruction. The inverse method applied to the reconstructing the spectral measure, in this case from electromagnetic data. Here's young, healthy bone with a much greater mass or area under the curve compared to the older osteoporotic bone. Okay, now more focusing on this spectral measure calculation. So I should say that there was a fair bit of work. So in complex analysis with basically Cauchy's theorem, that spectral measure is essentially the mismatch in the imaginary part of the function coming in from along the cut. And so there was a lot of work on very high resolution, very hyper accurate calculations of the effective parameters of composite materials in order to get your hands on that spectral measure through the mismatch in the imaginary part of the transport function. We took a very different approach. We did the dumb way, the kind of the brute force, just direct way. But it turns out that opens up all new kinds of possibilities that we had not anticipated originally. In other words, we discretize a composite microstructure, gives a lattice of ones and zeros, basically a random resistor network, and then that fundamental operator chi gamma chi becomes a random matrix. The randomness is from the randomness of the composite material of the brine inclusions, the ones and the zeros from the characteristic function. But now we have a matrix. We can compute its eigenvalues and its eigenvectors, and then we can actually construct. And that's a hard problem, of course, is when you get big sizes, computing all the eigenvectors and eigenvalues is a challenging numerical problem. But then we can directly construct the spectral measure. And one very important aspect of all this, those Stilts's integral representations are very general. The mathematical structure is the same for thermal conductivity, electrical conductivity, complex permittivity, all these different things, all these different parameters, all these different properties of a material, of a composite. So once you get your hands on the spectral measure for one property, like electrical conductivity, you can apply that in other words, now you have all the geometry information. You can put that into the Stilcher's representation for the thermal conductivity, for example. Now you have all that. So this is a really very powerful cross-property information.
Henry, are you fundamentally changing models here by going to a resistor network in what previously was a continuum?
This, in terms of calculation, it's not fun. I mean, in the limit, you're hopefully getting, some we have not proved that. I mean, yeah.
But that people generally believe that under...
Sure, sure. And there's all kinds of proofs, there's all kinds of rigorous models of proofs of convergence and so on. Okay. Yeah, for sure. Okay, so there's, we've done done a lot of image processing in the last few years with our melt pond work and now with these things. So conversion to two-component discrete microstructures. We use image processing techniques to convert these 2D fluid ice and bone marrow representations into these random lattice systems. Anyway, so there's the binary conversion, but then there's also the conversion into the lattices themselves. This is sort of the brine phase. This is melt ponds. This is the ice pack itself. So many different scales. That's part of the point here. Again, the integral representations don't care about the length scale. Okay, spectral. So here's a continuum composite. Here's a discrete composite. So actually, this is a pretty heavy-duty paper that kind of addresses some of the issues that you're asking about, mapping the continuum problem over to the lattice problem. And so here, here's the projection operator, projection matrix, this pointwise indicator function, and so on. This is the key resolvent representation. You apply this. There's a couple of different proofs for that beautiful Stilcher's integral representation. One is basically through Cauchy's theorem, and another, the most important way, though, is in some sense through the spectral theorem for self-adjoint operators on a Hilbert space. And this is the discrete version of that with the eigenvectors and so on. And so basically, we have this discrete series representation for the integral representation that we can then compute all these things with. Just some simple examples. I mean, this is not easy calculations, but these are relatively simple examples, though. The 2D square network, and these are some of the just spectral measure calculations, and they match up with certain known theoretical results. Again, the spectral measure is really the key mathematical object. One of the things about it is when you're below percolation, there's a gap in the spectrum. We got that rigorous bound that I talked about in PQ space associated with that. Spectral gap, and they collapse as you approach a percolation threshold. You see there's a gap, gets smaller, and it finally actually, it's hard to see here, but story here, 2 dimensions, 50% is the threshold, gap, smaller gap, no gap. That's a key mathematical feature of all this percolation theory in how it connects with these Stilcher's representations and the spectral measures. This is the brine phase, spectral measures, just spectral measures in the 2 different directions. Just again, these calculations. Okay, now here's the dumb way of calculating the spectral measure. This is one of the really cool things that it opened up. So here's melt ponds on the surface of Arctic sea ice, disconnected, just barely connected, really connected. These are some calculations of the spectral measures in the way that I've said, but again, I said that we had a random matrix for each realization of a random medium. We have a random matrix. We can calculate its eigenvalues and eigenvectors. We can start to look at the statistics of these eigenvalues. Now, there's a very famous area of pure mathematics, actually arose in atomic physics, called random matrix theory, the theory of random matrices. And I'm going to give you some slides on this, just stunningly beautiful mathematical phenomena where large classes of systems all exhibit universal statistics for their eigenvalues, and in particular for how the eigenvalues are spaced. And in fact, what one sees is a general repulsive phenomenon, namely where eigenvalues start to repel each other. In fact, there's a mathematical correspondence where they literally behave like electrons on a line in an external potential, and they try to repel each other. And this is really, in other words, the eigenvalues basically behave like electrons. And so, amazingly, what we found, first in this context, in this context of melt ponds, here we have disconnected melt ponds. Here's the so-called eigenvalue spacing distribution. They follow basically following a Poisson distribution, completely uncorrelated. When there's no long-range order in the system, they're decorrelated. But now, as we start to develop long-range order, the distribution is moving towards one of these universal distributions. And as we converge to the percolation threshold, here, as you get more and more connected, basically you're starting to match up with this, in this case, the so-called Gaussian orthogonal ensemble, one of the classical universal distributions that describe eigenvalue spacings. Okay, so a little bit about random matrix theory. Eigenvalue statistics of random matrix theory. So it was first found, Wigner and Dyson first used this to describe quantized energy levels for heavy atomic nuclei. In other words, for a big atom, are you going to really be able to calculate all the eigenvalues and really follow all that? No, you want to follow statistics of these things. And so Gaussian orthogonal ensemble arises in this case. So normal distribution 0 and 1, and then this is the associated matrix, the symmetrized matrix. Gaussian unitary ensemble in this case, the complex version, a unitary matrix. And then short range and long range correlations of the eigenvalues are measured by these statistics. And then these are just sort of some graphs showing some of the different kinds of universal distributions that arise in this way of looking at things. This random matrix theory has been successful in describing universal features of many disordered systems. This is atomic nuclei. One of the most fascinating to me is the most famous unsolved problem in pure mathematics, which is the Riemann hypothesis, that all the zeros of the Riemann zeta function, which is connected to prime numbers and so on, they all live on the line real s equals 1/2. But then how are they distributed? Well, they're distributed according to the spacing of the first billion zeros correlate with this Gaussian unitary ensemble. This is also a quantum chaos problem, and in the quantum chaos problem, in other words, quantum versions of systems that exhibit, like billiards and so on, that exhibit chaotic behavior, you see a transition in the eigenvalue spacing distributions. Now, just to give you an idea, sort of this is completely uncorrelated Poisson distributed eigenvalues moving over to more highly correlated repulsive eigenvalues, and then this would be the completely repulsed case where they're just all evenly distributed, so-called picket fence. Okay, and some of the transitional behavior that we see has also been seen in these quantum chaos problems, as well as energy level spacings for metal insulator, Anderson transition, and quantum conductors. And in other words, to me, this is a fascinating phenomenon that we found it in the context of sea ice in these spectral measures. I think is pretty interesting. And then to close this part of the discussion, here's again, this is the Arctic ice pack. The dark is the water. Here's just the spectral measures, and here you see again. Now we're tracking the water phase, disconnected, just becoming not connected yet, really connected. Poisson, moving away from Poisson, and then Gaussian orthogonal ensemble, this universal distribution. Okay, I want to talk a little about the eigenvectors, because again, very unexpected behavior. So this is disconnected spectral measure. This is sort of the electric field, or the logarithm of the electric field. And finally, when we develop long-range order, and basically in 2 dimensions, when we get the percolation threshold, and we're right on the money there, the Gaussian orthogonal ensemble, then we have extended states of the electric field as the system develops long-range order. This is measured by what's called the inverse participation ratio for an eigenvector, comes up in random matrix theory. And completely localized would be just 1, 1, versus everybody even, that's completely delocalized. In these ensembles, the eigenvectors are independent of this. Basically, you just get completely extended states. But then in the physics in solid state physics, condensed matter physics, in the so-called like Anderson localization for understanding flow of electrons and current in metals and semiconductors and so on, there are these mobility edges. In other words, you have on the energy axis, you have regions of extended states and mobility where you get conduction, bounded by these so-called mobility edges it's the edge of the electron's mobility. And we see that here. We see that in our case as well. Namely, the general picture for Anderson localization is with low disorder you get extended states. As you increase the level of disorder, there's a critical level of disorder where the wave functions localize. And we see a very similar picture, basically where delocalized extended states above the threshold, and then localization as you get below the threshold with too much disorder for the system. But we also see mobility edges as well. So these are some of these mobility edges that we see in the context for our matrix and spectral measures. Okay, now let's move on to the polycrystalline problem. Okay, namely here's homogenization for the two-phase conducting problem, same picture that you've seen before. And now we have all these individual crystals with, say, a particular orientation, and we might have information on the statistics of the, statistical information on the orientation of the individual crystals. We homogenize that to get an effective, say, conductivity tensor to represent the whole polycrystalline material. And so there's some really interesting math here in that we can, that whole framework that I just showed you through some kind of clever manipulations, we can take that, carry that over to the polycrystal problem. So here's the traditional two-phase formulation where these characteristic functions, the sum of them equals one. That's one in the ice, sorry, one in the brine, 0 in the ice, 1 in the ice, 0 in the brine, and they satisfy this property here, this Kronecker delta property. And then here, again, here are the basic equations. But then in the polycrystalline problem, this gives you, so there might be like a uniaxial situation where you have a conductivity in one direction and then the same conductivities in the other two directions. And then there's like a rotation matrix that gives you the local conductivity tensor, which can be written then in terms of these two matrices, x1 and x2, not chi1 and chi2, but x1 and x2, that have these same properties. And it's through that connection that we can then carry over the proofs of these Stieltjes integral representations. Yes?
What's x1? Is it the gradient of the...
No, x1 and x2 are just matrices. If it's a vertically oriented crystal, x1 is going to be 1, 0, 0 with all zeros, and then the x2 is going to be 0 with the ones there. Yeah, so they're just matrices. Okay, and so you'll recall this looks just like the resolvent representation that we had for the classic two-phase case, where the parameter S is just but now this is for an individual crystal, and it's the same projection operator. But now we can go through the same proofs and derive the same, it looks the same, but it's not. Now it's the spectral measure of the self-adjoint operator x1, gamma x1, and the mass of that measure, the area under the curve, is the average orientation. And again, the higher moments depend on the endpoint correlation functions of the orientation statistics. Okay, and we just published this. This was on the cover of the Proceedings of the Royal Society, I guess published somewhere around here, where we basically derived these Stieltjes integral representations for the effective complex permittivity for polycrystals. We got forward and inverse bounds. We applied it to sea ice using two-scale homogenization that I'll mention in a second. And then we developed an inverse method for distinguishing ice types, which you might be interested in, for distinguishing different polycrystalline, different grain structure, basically, electromagnetically. Two-scale homogenization, I'm thinking of in terms of, here's an individual crystal. We numerically homogenize that to get the unit complex permittivity tensor, and then we plug that base tensor into the analytic continuation method to then derive, for example, rigorous bounds on the complex permittivity given, say, the average orientation and other information like that. And we can, of course, and we invert that as well. But now, of course, because of the way we've done this, we can compute those eigenvalues and eigenvectors for the spectral measures for the polycrystal problem as well. And again, we see all sorts of fascinating behavior in that here, these are spectral measures associated with these kinds of orientations of the underlying polycrystal anyway, with following these distributions, and there's just a parameter delta there that is going across there. And then also, in a purely isotropic case, it turns out that the eigenvalue density matches up with a well-known, although this is not exact, and this is just numerical at this point, but the eigenvalue density seems to match up with a so-called famous random matrix ensemble called the Jacobi random matrix ensemble. Okay. All right, now again, let's turn the page, but let's continue down this road of developing powerful integral representations for homogenizing important problems. Now we're going to deal with the advection diffusion problem. Yes?
Ask a sort of physics question.
Yes?
I don't understand this, but your homogenization technique involves this energy. Is that a physical energy?
Absolutely. Absolutely. There's different formulations of the problem. One of them does not involve energy, but one of them does. And that energy is the one that comes up in the variational principles, which were the original basis for deriving these bounds.
So really,
In the real case.
real energy, and it really has some variational minimum.
Yes. Okay, so now again, let's try to do these very powerful integral representations, but for advection diffusion, which plays a key role in the transport, say, of pack ice. These are all pack ice pictures, but of course I would imagine that you guys are interested in advection diffusion, or the flow of heat or whatever, not just diffusive, but with fluid helping to move it around and so on in your problems. And the advection can, of course, when you get a cup of coffee and you want to cool it off, you don't just let it sit there, you kind of stir it around to help the transport of heat. And so tracers, buoys diffusing in ocean eddies, diffusion of pollutants in the atmosphere, salt and heat transport. So here's the basic advection diffusion equation for a divergence-free velocity field. And then the idea is that you homogenize this, and there's all kinds of proofs of the existence of an effective diffusivity, which is the enhanced diffusivity that takes into account all the geometry of the flow field. And here's some ocean problems and all these currents and so on. And now actually, so Andy Maida and Marco Avellaneda, a long time ago, they developed a Stieltjes integral representation for this effective diffusivity directly based on our proof, with my proof with Papanikolaou in communications and mathematical physics, for the classic two-phase problem. And anyway, so they kind of stopped at getting some bounds and so on, but now we've picked that ball up and taken it a lot further. Now, this is just a little about the homogenization. In other words, you have a particle diffusing in here, and the idea is you replace that with some enhanced diffusive process that was, in other words, with the effect of the velocity field. And again, now this is, again, the parallels with our original formulation. So here's the advection diffusion equation, homogenize it, but now you can also write the effective, diffusivity in terms of this energetic type of term. And then you can, in other words, you can write this in parallel, again, with the quasi-static Maxwell equations, at least in the steady state case. And then, in other words, just writing down the similar kinds of things, similar kinds of terms, and this is in 2 dimensions, the stream function in general is an antisymmetric tensor whose divergence gives you the velocity field, and then that operator becomes with this in the time dependent case. And anyway, so again, you derive these resolvent formulas, and this then is sort of the fundamental relation involving this guy that you get the resolve. So that's the electric field that corresponds in our case. And then this is the Stieltjes representation. So that's the key integral representation here. And there's a lot of interesting things about this. In the original Avellaneda-Maida approach, the spectral measure, the parameter involved the Peclet number, which had information about the velocity. So the geometry of the velocity field, or the composite, was not completely separated from the parameters, like the fluid diffusivity or whatever. We've now done that. That's one of in other words, that only is the local diffusivity of the fluid. All the geometry information now is contained in there and nothing in there. So we've really accomplished the separation now. And actually, just to show you kind of how the parallels of at least the original Stieltjes representations, there's ours, and then I've manipulated Marco's and Andy's so you can kind of see the direct correspondence, and then the T, that's involving the Peclet number. And so we've done computations of spectral measures and effective diffusivities for a lot of model flows. We've also, and one of the beauties of what Andy and Marco did was by establishing the Stieltjes representation, they can start to get rigorous bounds on the effective diffusivity. And anyway, we've started to look at that as well and applied that to the case of sea ice. Here's just a few sample kind of calculations. a cat's eye flow and a BC flow. And again, and we do not understand this, but the eigenvalue spacing distributions for the cat's eye flow seem to correspond to the, correspond to the GOE, Gaussian orthogonal ensemble, and for the BC flow, the Gaussian unitary ensemble. Anyway, again, just opening up a whole nother world to investigate and why these things are the case. Again, here's just some spectral measures here. These are calculations for a cat's eye flow, and these are all in that Gaussian orthogonal ensemble situation. And these are the spectral measure calculations themselves. And we hope to go a lot further down this road because it's a very interesting one. Now, specifically to sea ice, and something that may well be of interest to you guys here, thermal conduction enhanced with convection. And again, in our case, there's a large temperature gradient. Temperature on the top surface driven by the atmosphere, the bottom surface in contact with seawater at minus 1.8 Celsius. There's the advection diffusion equation, but now with the right parameters for the sea ice problem, bulk density, specific heat, temperature dependent thermal conductivity, and so on. And then, so here's some of our results there. These are the bounds. That's like kind of like the arithmetic mean bound, that bound right there. Let's see, these dots are simulations of just purely diffusive, no enhancement due to convection. And then there's our simulations with, where we include a two-dimensional velocity field similar to what you might see in sea ice. And then there's some actual data on the thermal conductivity of sea ice, sometimes in the presence of convection. And we actually have just submitted a paper on inverting all this, or just about to submit a paper on inverting a lot of this to recover thermal conductivity parameters in the context of convection-enhanced diffusion. This is the brine velocity field that we use, sort of slowly upward and then these plumes downward, kind of. Anyway, this is a typical kind of convection, possibly convection pattern. Okay, and then I think the last slide I have in this little section, here, and then I'm just going to get the last little section on melt ponds. What about fluid flow, thermal transport, and convective processes in the porous microstructure of sea ice on Europa? So Europa is believed covered by deep briny ocean with a thick icy crust. And so, near the top, it's all obviously frozen, no fluid. Down at the bottom, it's all fluid. There's got to be a percolation threshold somewhere in there. There's got to be convective processes going on. It's got to be really interesting. I always, in my calculus classes or give lectures to undergrads, I say, okay, who wants to come with me to Europa, to core the ice there, That's what I'd love to do. Also, the algae and the bacteria that live in the brine inclusions of sea ice, that's sometimes thought of as a proxy for possible life on Europa. In fact, I remember, I forgot when it was, but there was some probe that was going to crash, and I think they crashed it somewhere else so that it wouldn't affect, that it wouldn't contaminate. Cassini, okay, yeah.
Landing on Saturn next year.
Okay. Oh, okay, that's the end of this one. Now I just got to switch over to the very last one. Okay. Okay, just a few words about our experiments. So we've been developing electromagnetic methods of monitoring fluid transport and microstructural transitions, and as well as doing extensive measurements of fluid and electrical transport properties. I believe that our measurements of fluid permeability in sea ice are probably a lot simpler to do than yours. What you guys have to go through. So here you see we've had an extensive field program over the last 8-9 years or so. Okay, here this is the notices of the American Mathematical Society. This is me doing. I believe these were the first measurements ever done of the fluid permeability in Antarctic sea ice. And basically the idea is you drill a partial hole, there's a pressure head created, and so the water wants to fill back in. And so how rapidly that water fills in tells you the permeability of the ice right at the bottom of the hole. And so basically I got started by this with my ruler and a watch. I would call it my $1 million meter stick because all my colleagues had millions of dollars of fancy equipment, and I was working with a stupid watch and a ruler. Worked pretty well though. It actually worked. And actually this looks like they're doing very heavy duty science, but they're actually playing soccer. Okay, now one of the things I had conjectured a long time ago in the original science paper was that the percolation threshold for granular ice, this more fine-grained granular ice where the brine phase is more randomly distributed, should be a lot higher. I think I said 8, 9, 10%, something like that. than the nicely segregated brine inclusions of columnar sea ice. That was originally conjectured that in 1998 we finally at least have a draft of a paper. It took a long time. You have to be in the right place at the right time with the right equipment. Polar field science is tough. I mean, it's not as tough as actually burrowing down into the mantle and really seeing what's going on, but it's not easy. So anyway, so there's the 10%. We finally co-located our permeability measurements with our crystallographic measurements. We got a hint of all this in 2007, but we had to go back in 2012 to really nail it down. We have the same universal, it's this the way percolation theory should work. Same universal critical exponent that describes the takeoff above the threshold. It's just, and the same constant in front, it's just the threshold is different. It's a 10% versus 5%. Now, we've also looked at the electrical signature of this. And again, I didn't have much background in this, so I kind of did the dumb experiment that nobody else had done because they thought you'd leak too much. Based on my knowledge of the microstructure of sea ice, I certainly knew that the dramatic effect would be in the vertical direction. The problem is that, to my knowledge, most of the other methods for looking at the electrical properties of sea ice were surface-based measurements. So the vertical and horizontal components of the electrical conductivity are mixed up. So I wanted to isolate the vertical component. So my idea was to extract a core, lay it out, now measure the conductivity just with 4 nails, and it was actually a classroom resistometer or something. It was very rudimentary methods. And here you can see it. Those are nails and that's wood, and these are just wires. And but I'm measuring the vertical component, and amazingly we see this fantastic behavior. There's the resistivity diverging at 5%, same critical exponent. We can calculate these coefficients in the front. We see this both in the Antarctic as well as the Arctic. So again, this is the electrical signature of the rule of 5s. And then we can take these results and then apply this to so-called cross-borehole tomography, led by my New Zealand colleague Malcolm Ingham, where you freeze in vertical electrode strings, and then you're essentially reconstructing the complex permittivity structure in the box inside. And so this is like before melt ponds, after melt ponds, and you can electrically classify the different layers, like impermeable where ponds can grow, impermeable for CO2 exchange, but it's still impermeable enough for surface ponding, and then highly permeable CO2 pumping buildup of nutrients. And anyway, so there's a lot of interesting biology and physics that goes in to inverting, again, this electrical data for important physical and biological processes. Okay, and then finally, we've been looking at these fascinating melt ponds on the surface of Arctic sea ice. You don't really see them in the Antarctic. It's not completely understood why. Maybe people think, well, there's so much more snow in the Antarctic. They're there, but you kind of don't see them, and they might evaporate. There's different explanations, and I've never seen a definitive answer as to why you see them in the Arctic but not in the Antarctic. But these are major drivers in polar climate. These determine, the dark light determines the albedo of the ice in the all-important melt season. And so these are very important things, as I mentioned at the beginning, very important to understand and their evolution. And there have been very detailed numerical models of the evolution of melt ponds, again, kind of like global climate models, incorporating all the basic physics, including our permeability results, which determines whether or not they're draining or not. But being in a kind of a statistical physicist, I wanted to step back from this and ask, well, are there universal features of the evolution of melt ponds, which are similar to phase transitions in statistical physics? And of course, when I looked at this, I say, oh, that's a fractal. And what's its fractal dimension? Nobody had really asked this question before. So just a little primer on fractals. These nice simple curves, one-dimensional Euclidean curves. Start bending it up, Koch snowflake, fractal dimension 1.6. Within if a curve is moving in 2 dimensions, the maximal fractal dimension would be 2 for so-called space-filling curves. This is a regular one. This is Brownian motion in 2 dimensions. This is a so-called Hilbert curve, or a piano curve that was popularized by Hilbert. And so then, motivated by some work by Lovejoy on clouds, who used area perimeter data to find that cloud and rain boundaries have a fractal dimension of about 1.35, No, it's based on how the perimeter scales with area, basically. And if the perimeter is growing so fast, you're starting to develop a fractal type behavior. And we thought we'd see something similar for melt ponds, but we saw something much more interesting. Now this is the logarithm in logarithmic variables, and so the slope of perimeter versus area, so the slope is the fractal dimension. So the moment I saw this picture, I knew we had something really cool, because we have a change in the slope. That pond right there for small, that's a simple Euclidean pond, a transitional pond trying to become self-similar, and a fully complex pond with a self-similar boundary that's trying to behave like a space-filling curve. And here's a plot of the fractal dimension as a function of length scale. Starts off at 1, goes through a transitional regime around 100 square meters, and then flattens out at about 2. Okay, we've come up with a lot of models for this. We have a lot of work going on this melt pond problem. There's a percolation problem, disconnected, just barely connected, really connected. We actually have a large project going on. This is part of a Office of Naval Research project looking at the percolation properties of this, and this is being led by an absolutely brilliant high school student. I've been very lucky I've had about 7 or 8 of them working with me. That every single one of them has gotten into Yale or Princeton or MIT or Caltech, or these kids are just amazing. And this guy is actually leading this project. And on the percolation properties of this. Now, as you look down, there is an issue of, how connected they are, and this has to do with the drainage properties, and whether or not high connectivity of melt pond networks allows vast expanses of meltwater to drain down seal holes. There really are seal holes, these thaw holes, these little vortices, and so on. You got to be careful of these. Look at this picture. There's my friend Hayo, who we work together very closely. And one step, you're dead, you're gone.
The seals make the holes?
The seals make the holes, and they keep them up so they can get up. But then those serve it drains, and you see these large areas that have all these patterns that drain through the seal holes. Okay, so we've just had a paper published in Cold Reason Science Technology where we develop image processing techniques and algorithms to map images of melt ponds onto random resistor networks, and then we can compute the effective conductivity of these for looking at is basically horizontal flow, where the edge conductance corresponds to the neck width, and then we can compute a lot of the properties of these and the conductivity of these graphs and so on. Another very beautiful model, in fact, this is now in submission with Journal of Fractal Geometry, is we came up with these basically surfaces like a random surface, like the topography of the ice, and then the water level just goes up and down. So there's no other physics going on, although we've compared that it's not a trivial model at all. It took a long time to find surfaces that actually did the right thing so that we really got the right fractal properties. These are typical melt ponds and how they evolve in this. I actually have some movies up, but I won't show you those. But we're able to see the transition in the fractal dimension, and all the, really correlates with what we actually see in reality. Another approach we've taken, again, this is another high school student, I think she's in her 3rd year at Yale now, and this is a so-called voter model, an interacting particle system model, where in a lattice model, you may or may not vote, depending on how many of your neighbors vote for some candidate or something. If you get along with them, you might vote like them. If you don't like them, you might vote opposite. Anyway, these kinds of rules. And in our case, a square is more likely to melt depending on how many of its neighbors have melted. And so we can watch this evolve into these melt pond types of shapes. And again, we don't have a length scaler. This is a more abstract model, but we see this transition in the fractal dimension. And then finally, the model that I'm really excited about, that we're basically finishing up, but we have amazing predictions from this, just from the most rudimentary physics, is an Ising model. So this is the most widely studied model in statistical physics, I'd say, originally developed to look at the Curie point in a ferromagnet. And so you basically have the energy of the system, you have either spin up or spin down, and the spins, they interact with each other, just their nearest neighbors. The nearest neighbor Ising model is the classic one, and then they interact with the applied magnetic field. And I'm not going to show you the actual Hamiltonian that we write down. It's somewhat involved. But then again, the Hamiltonian, the energy of the system that we write down, only involves the most basic thermodynamic parameters. The thermal conductivity of the ice and the water, the latent heat of fusion, just the most basic things that you would, that you could put into this model. to write down like a toy model, like I was talking about before. In fact, some of my motivation for the way we wrote this down was based on the beautiful Eisem and Wetlaufer tipping point paper, because they just have a lot of the similar kinds of terms going on. The magnetization is just the sum of all the spins, the average sum of the average spin in the system, and that's basically the pond coverage. And these are actual runs of Ising models that look like melt ponds. And in this case, the melt ponds are clusters of magnetic spins that align with the magnetic field. And just recently, well, I should say that anyway, we minimize an Ising-Helmholtzian, and it's really like a random magnetic field. That's kind of like the topography. And anyway, we can incorporate ice albedo feedback by coupling constants and so on. But anyway, but amazingly, just with the most basic thermodynamic parameters, and and kind of a toy model like this, we can predict the transition in the fractal dimension. The closest real number that we've been able to measure from our real data is 86 meters squared, where the transition occurs, and we can predict, again, for this Ising model, that the transition occurs around 70. So that's really, given that there's 4 orders of magnitude of data, that's really close. And also then, the other key iconic measurement that appears in the melt pond literature is the pond size distribution exponent, namely the probability of finding ponds of a particular area. And we're right on the money in terms of what's observed for the kind of ponds that we were looking at versus what our Ising model predicts. Okay, so then in conclusion, I'm going to show you the video just right now, but let me just go through these brief conclusions. So as I mentioned at the very beginning, summer Arctic sea ice is melting very rapidly, and ultimately we need to improve our understanding of sea ice and its role in climate. And in particular, of interest to people here, fluid flow through the sea ice, which we've studied in a lot of depth, mediates many processes that are important both to climate change questions as well as ecosystem questions. And in particular, in this context, mathematical models of composites and statistical physics that we've used to study sea ice may give some insights into this partially melted situation that you guys are interested in, I hope. And in general, homogenization and statistical physics help to address this fundamental challenge of linking scales, and they provide rigorous methods for finding effective behavior, and ultimately we're advancing how sea ice is represented in climate models. And from my perspective, I mean, most math professors don't go to Antarctica and get out on the ice and tangle with the penguins and the killer whales and the leopard seals and so on. But from my perspective, these field experiments are essential to developing not just whatever mathematics, but really relevant to the problem at hand. It certainly played a big role in my own career. And then ultimately, we hope that our research will improve our projections of climate change and the fate of the Earth's ice pack. And I need to thank the NSF and the Austin Naval Research. And we also have this big math climate research network with like 12 nodes across the United States. The whole idea is to bring young people into mathematical climate research. And so with that, now I'm going to hopefully, now entertain you a little bit with a video that I produced. Every big Antarctic expedition I've been on, I've tried to ultimately produce a video, because I think it's important to bring that experience to students and to people. Most people don't get a chance to go to these places. So, oh wait, actually one more. There's one more picture I wanted to show you, because it's not in this particular video, but this is interesting, I think, to you. This is I started doing tracer experiments. The Australians love beets, so I started doing beet with beet juice. You turn a block of ice upside down, and then look at this. These are the channels, and then I eventually graduated to like fancy dyes and fluorescence and so on. But anyway, and we actually there should be a paper coming out all connected to the granular ice problem with this, because it all matches up really, really well. Okay, so let's get rid of that. Whoops. Okay, so now I'm going to show you the video. Being in the Antarctic. $10,000 composite core that I have. Yes, it's broken.
Welcome back. A professor of mathematics and 2 grad students from the University of Utah are preparing for a hazardous 2-month mission to Antarctica.
Well, why do they need mathematicians in Antarctica? Science and nature specialist John Hollenhorst is live at the U right now with the answer. John?
Well, they're heading out in about 2 weeks. They'll be shipping out on an Australian icebreaker that's steaming out of Tasmania. For one of these math whizzes, this is his 15th trip to the polar regions. Yes, he'll be crunching the numbers as well as crunching the ice.
So this is in Hobart, the home port of the Aurora, just getting the ship ready to go. It's a pretty big process, as you might imagine. Now we're crossing the Southern Ocean, and I was a little disappointed. It was very calm. I love big waves. Anyway, we're entering into the marginal ice zone. Spectacular morning, icebergs and beautiful sunrise. These are these waves propagating through and they break up the ice pack, and that's a very important process. Here you get a sense what it's like down on the ocean. These big hunks. Now look at the entire ice scape is just undulating. It's a
What do we have here? What are you trying to do?
Wave buoys that we're sticking out on the sea ice in Antarctica, and the idea is to measure the wave decay. Because we're interested in how the wave energy propagates in sea ice and how that affects the breakup of the sea ice melt, therefore. And our sea ice plays a kind of big role in the climate system, and if we can predict how it breaks up and how it melts and how it grows, then we can improve the climate levels.
What did you study as an undergraduate?
Mathematics.
What did you do your PhD in?
It was applied mathematics PhD, studying wave scattering in sea ice.
So what's been your favorite part of being down here?
I'd like to say the waves, but that makes me a bit seasick.
Okay, now this is setting up our first ice station, and you see it's all nice, smooth, beautiful ice. However, we're still in the marginal ice zone. There are still waves propagating through here. And these penguins were coming to warn us, like, you idiots, what are you doing? When we were out here, I could see those orange bags moving up and down, and we contacted the chief scientist. Anyway, everybody was pulled in, but it was too late for them. They got stuck on the wrong side. There's the penguins laughing. I was on the incident response team in the first responders group, and this was the first time that little bridge had been brought down and actually deployed, and then they were really lucky that they were able to just simply cross there, and now they've been saved. Now they're coming back. We had to go out and gather up the things, but all of a sudden the ice just started breaking apart just a few minutes after we finished. And anyway, this is what the oceanographers use to measure conductivity and salinity and temperature.
It's instrumented with 5 cameras, so we
that's a big drill.
Can surface of the ice, look at physical features, but also can observe the biology. And my instrument, or the main goal, is really to measure under ice irradiance or transmitted sunlight and the color composition.
So this is underneath the ice, like a different world.
They are in the ice, so we're working on algorithms or equations.
This is the crunched up ice, how thick it can get.
It's a proxy for algae biomass in ice with the amount of light.
Now we're going to see a little bit of our work, and this is with 2 students, David, a math student in electrical engineering. It's about 2 hours to get all this ready, to get out on the ice. That's me shoveling snow. I did a lot of that, because we got to get to the ice surface. Here I'm drilling these are packers to keep the horizontal flow out. So there's a lot of what I call Home Depot science. Well, in the U.S. we have Home Depot, hardware store.
While I break it with this very specially chosen instrument, this bamboo
The core is supposed to get the core, but it doesn't always work. So we had to develop this lasso method to pull the core out. And that's beautiful.
Perfect core.
Here's the fluid flowing in. We want to measure that rate.
Looks like we're doing piping and plumbing out on the ice.
All this stuff is from hardware stores and garbage dumpsters.
Pressure transducer down here, and then we have one that sits in the atmosphere as well.
This is
and
reservoir
by seeing
technology.
What pressure it actually experiences compared to the outside air, we can tell how much water is actually in the hole.
So it measures the data. It's constantly measuring how fast, and then we recover that data after we go in at night. We're always being approached by SEALs.
This is a block of ice that we're going to put in this waveguide to do a microwave measurement.
Some of our electrical measurements. So we're always being visited by emperor penguins. They're the big ones. They're pretty big. This is working inside the freezer, doing our crystallographic work in the freezer on the ship in Antarctica.
You can see these sort of round crystal grains. Then there's a transition at about 20 centimeters where we see it still looking fairly granular or like snow ice, but we start to see it turn into columnar ice.
So here we were finally joined by a little Adelie penguin. And then an emperor joined the party, which is kind of unusual. Anyway, then we took the party back onto the ship. And that penguin can do calculus too. This was springtime in the Antarctic.
Well, so the primary objective is to really get a good assessment of the full 3D topography of the underside of the sea ice. This is all going to feed back towards the holy grail of the sea ice world in terms of being able to monitor and assess things like sea ice thickness from remote sensing packages like satellites.
Fluid dynamics. Now we're going to look at a laser scan of the snow surface. That's Gerhard Dieckmann, a famous sea ice scientist, being scanned. And this kind of looks like the ghost ship Aurora Australis, like in the Pirates of the Caribbean. Who knew penguins slapped each other? And here's the disapproving mom. That's a minke whale. I guess the most common kind of whales down there.
The Antarctic supply ship Aurora Australis is stuck in heavy ice.
So we got stuck
the icebreaker
for about 3 weeks.
1,600 nautical miles southwest of Hobart, close to Casey
A year
Station.
later, there was a famous Russian tourist ship that got stuck.
Career path for someone who wants high adventure in remote parts of the globe,
and the Aurora was
like
involved
Antarctica.
in the rescue.
But it's turned out that way for University of Utah math professor Ken Golden. The media in Australia are reporting that the 50 scientists are in no danger, waiting for the weather to change. In fact, they're taking advantage of the situation, helicoptering off the ship to do studies.
See, there's radar slung underneath there for some of the electrical experiments. Probably the only Halloween party ever conducted on the Antarctic ice pack. There's an alien there, you see. Now, we were stuck for a long time, but this guy got stuck as well. That's the whale. You see how thick the ice is. That's why we were stuck. Basically, the wind blew the ice up against the coast. It took us, we finally got a lead. 800 meters took us 2 days of backing and ramming to get to the lead. So he's testing the water temperature with his face. Oh, too cold. They might be trying to escape a leopard seal, who knows, or a killer whale or something. This is a raw seal, like a mom with her pup. So we were so late, it was going to screw up the Australian shipping season for Antarctica. So they really went fast. We crossed the Southern Ocean, I think, in 4 days. It was certainly the fastest crossing I've ever seen. Now this is cool. That's a big leopard seal, top predator, in these massive rollers going through the marginal ice zone. Now this is one of the greatest days of my life. Hurricane force storm in the Southern Ocean, massive waves. I was happy as a clam. Now remember, this ship is 300 foot long. And look how it's being tossed around. The next shot, I'm right down there where you're definitely, I was not supposed to go. And that's what I was looking at. And I finally got, oh, sorry, what? No. I got soaked. Anyway, we finally returned to Hobart on a beautiful rainbow-filled morning. So thanks very much for listening.
Got a quick question, we can do that, but I think maybe in the interest of time, we should retreat to the reception and you guys can quiz Ken there if you have further questions. Yeah. Oh, all right. Oh, okay. All right, let's thank Ken.
Okay, thanks for that.